Hello, everyone. Welcome to my talk, and thanks again for Robert's kind invitation and kind introduction. And the title of my talk is Catalyst Structure and Composition at Realistic Conditions. And the work I will talk is from both my postdoc time in Catalysis Theory Center of the Technical University of Denmark and my PhD time Nomad Laboratory in Friedrichshaber Institute of the Max Planck Society. The processes which occurs on the surfaces plays a critical role in the manufacture and the advancement of the performance of advanced materials. Examples are heterogeneous catalysis, surface segregation, and crystal growth, etc. As illustrated in the left figure, you can see that this is an example of carbon dioxide reduction to the carbon monoxide. And the reaction involves absorption of the CO2 and hydrogen on the catalytic surface and diffusion around the surface and the react of the absorbed species to produce carbon monoxide and water and desorption of the product. And on the right movie, you can see this is a scanning tunneling microscopic about the individual oxygen atoms on the dense layer of CO or ruthenium 001 surface. And we can clearly see how the surface restructuring under reactive conditions. And therefore, it is crucial to study the chemical dynamics of the surface and in particular the chemical reaction steps and the transport processes on the catalytic active surface. And to reach a microscopic understanding of these processes, the prerequisite is the detailed information of surface stoichiometry and geometry under realistic conditions. In the following, I will first introduce the state-of-art approach, ab initio atomistic thermodynamics, and which is widely used in the community to determine the surface stabilities in the reactive conditions. And the second part of my talk is mainly to introduce our recently developed method, the replica chain Gray-canonical approach, which provides the ab initio description of the surface restructuring. The ab initio atomistic thermodynamics has been widely used to determine the surface stoichiometry and geometry under realistic conditions. It was first introduced by Matthias Scheffler and later reviewed by Carsten Reuter and Matthias Scheffler for the solid surface. And in this approach, consider the surface, this slab, in contact with oxygen environment. And the surface can take any amount of oxygen or give any amount of oxygen, exchange the oxygen with the environment without changing the temperature and the pressure of the environment. The appropriate thermodynamic potential to describe the system is the Gibbs free energy of absorption, which can be calculated by the Gibbs free energy of the whole surface minus Gibbs free energy of the clean surface and minus the number of absorbed oxygen times oxygen chemical potentials. The Gibbs free energy can be calculated by partition function, and for the ideal gas approximation, the partition function can be the product of the individual partition function. For instance, the translational one and rotational one, vibrational one, and the electronic ones and configurational partition functions. And here in this method, the solid surface also follows the similar approximations. So the Gibbs free energy of the solid surface can be the sum of the individual contributions. That is the total energy of the surface and the translational free energy, rotational free energy, and vibrational free energy, configurational ones, and a PV term. In practice, in this method, the total energy of the surface provided by density functional theory calculations and the translational and rotational free energy are usually discarded due to the solid systems. And the relative vibrational free energies between the the whole adsorbate and the clean surface are largely canceled out or treated at harmonic approximation, and the configuration of free energy is neglected, so is a PV term. When it comes to the electrocatalysts, as illustrated here, that is the simplest model of the solid-liquid interface. For this is a cathodic surface with a sorbed N2 molecular, and one is a proton transferred to the N2 and became N2H species. And if we want to have a qualitative prediction for this kind of system, for the first principle calculations, it's become very complicated and even more expensive, or hardly can do this, since that first of all, we have the solvent and the solvent dynamics, and secondly, we also have the surface which is electrified by the applied potential. So the surface is a charged surface, and the solvent and the dissolved ions try to screen the charged surface and form the so-called electric double layer near the cathodic surface. And instead of modeling the whole system, but a small part of the system, that is a finite system, we treat the system like a finite system in contact with different reservoirs. And these reservoirs provide species and charges to the finite system. So the Gibbs free energy of this finite system can share the similar equations with that of the Gibbs free energy to describe the interface between the solid and the gas phase. Besides, there's a reservoir of proton and electrons. And one of the very simplified but widely used method named computational hydrogen electrode, which is introduced by Jens Noskroff and Ye Rosmail. And in this approach, the reservoir of hydrogen and the reservoir of the proton and the electrons is equal to the standard hydrogen electrode. And so the chemical potential of the proton and the electrons, this sum is equal to the standard hydrogen ideal gas with the proper applied potential and the pH corrections. Here, the applied potential is serve as a reservoir for the electrons, and the pH serves the reservoir for the protons. Before I give an example of this computational hydrogen electrode, I want to give some background on my current project about the ammonia synthesis. And ammonia is a basis for the fertilizers, and is also the ideal carbon-free fuel. And the ammonia now currently is solely synthesized based on the Haber-Bosch process, and it has been calculated the food of half of the population is based on the Haber-Bosch process. Despite its significance, there are several drawbacks for the Haber-Bosch process. First of all, it operates at harsh reaction conditions, that is high temperature and high pressures, which result in the large-scale centralized productions. And more importantly, the reliance on the natural gas to supply hydrogen will give massive CO2 emissions and the large energy consumptions. Alternatively, electrochemical nitrogen reduction reaction provides an extremely interesting substitute to the Haber-Bosch process. It operates at the mild reaction conditions, and the hydrogen can be provided by water, and the electricity can be provided by the renewable energy like solar or wind. And this will result to produce the green ammonia and synthesize ammonia in a sustainable way. Nahowever, the electrochemical ammonia synthesis has the main challenges, that is a low selectivity, named as a Faraday efficiency, that the fraction of the electrons towards to produce ammonia. As calculated, as shown here, this is a calculated limiting potential of the nitrogen reduction reactions, the black dot, and the hydrogen evolution, the red dot, as a function of nitrogen binding energy. And we can see that the limiting potential for the nitrogen reduction reaction is more negative, always more negative than the hydrogen evolution, which results that the production rate of hydrogen is exponentially more than the nitrogen reduction reaction. And also experimentally, Professor Checkendorf and his group did this isotopic labeled experimental and validate that the ammonia produced in the lithium-mediated process is the only one that the ammonia from the nitrogen reduction, other than the other pollutants. And this is a lithium-mediated processes. And the non-aqueous solvent THF contain lithium salts and the proton shuttle ethanol. And once the reaction starts, that the lithium cation is electrodeposited on the cathode surface, and the metallic lithium is very active to decompose the organic solvent and forms a solid electrolyte interface layer. This is a concept which we borrow from the lithium battery. And once the solid electrolyte interface is formed, that the lithium cation, proton, and nitrogen transport from the bulk electrolyte through the solid electrolyte interface and approach the cathode side. And metallic lithium can split the nitrogen immediately. And the nitrogen species is further hydrogenated with the coming protons to produce ammonia. And the current state, the current development of the lithium-mediated process is the Faraday efficiency is close to 100%, selectivities and the high production rate at 1 amp per square centimeters. But there are still challenges. For instance, on the anode side, and before that, we always THF oxidations that produce the protons for the ammonia synthesis. And we want to have a new cells that use the hydrogen oxidation to produce the protons, because hydrogen can be produced from the water splitting, and so that in this way that ammonia produced in the sustainable way. And our experimental colleague, Dr. Xianbiao Fu, first tried use the platinum, which known as the most active catalyst for hydrogen oxidation reaction in the aqueous system. But he found that the catalyst, the anodic potential immediately beyond 1 volt, and the catalyst became deactive and start to burning the THF. While when he used the platinum gold, the anodic potential is keep around 0.3 volts, and the other experimental colleague, Dr. Jakob Peterson, he used the isotopic labeled studies measure the ammonia accumulation over time and see the deuterium labeled ammonia increase with the increased time, which proves that the platinum gold is a good catalyst for the hydrogen oxidation in the organic solvent. As a theoretician, we want to understand the mechanism of the hydrogen oxidation in the organic solvent. As shown here, this is the current density as a function of the hydrogen absorption energy, and we found that the platinum gold catalyst has a similar hydrogen oxidation activity with that of pure platinum, while the dissociation barrier of the CH and the CO species has a considerable value on the platinum gold surface, but very fatal on the pure platinum, which means, as we all know, that the platinum is easily poisoned by CO. So with the produce of the CO, that the pure platinum became easily poisoned, but the platinum gold reduced the CO production. And further, we investigate the selectivity of the platinum gold about the hydrogen oxidation and the THF oxidations. And two pathways are selected for the THF oxidation. The first is the direct dehydrogenation from THF to furan, and the second is involving water to produce succinic acid. And we could see this is the turnover frequency as a function of the applied potential, and the platinum or the platinum gold, the hydrogen oxidation selectivity is enhanced. More importantly, we want to see whether the catalyst has some reconstructions or under the reaction conditions, and we further check the stabilities of the platinum gold surface in a trace amount of furan, CO, and CH species. And we found that even a small amount of furan or this CO or CH species, the platinum will segregate to the surfaces. And the experimental angle solved XPS also revealed that the platinum gold surface ratio is increased after the experimental. And this will, in the end, the surface will form the platinum overlayer gold substrate. And we found that this platinum overlayer gold substrate has a similar HOR activity, which maintains the HOR activity while further suppress the CO poison, since that the dissociation barrier of CH and CO became considerably large. It became impossible to produce CO. Then come to this method, both for the thermal catalyst or for the electrochemical catalyst. And what we want to do is that in the state-of-art method, these two approximations however, is not always give a accurate phase diagram or surface stability estimation, especially in high temperature or high coverage. And we want to free from these two approximations, which required an unbiased sampling of the configurational and compositional space. And the sampling of this surface in equilibrium with the gas phase or the liquid remains challenging. As shown here, this is 3D potential energy surface. It contains numerous minimums and a large free energy barrier to overcome. And more importantly, for the many particle systems, the particles is very hard to diffusion. So there's a diffusion bottleneck for the sampling methods. And when considering the surface in contact with liquid or gas phase, the stable surface structure is a statistic average over the absorption or desorption processes, the exchange of the species with the reservoirs, no matter this reservoir is gas or liquid. And we think the Greg-canonical ensemble is also a natural choice to describe this system. And moreover, it is also straightforward for Greg-canonical ensemble to extend to multi-component systems by adding the chemical potentials of another species. Indeed, Robert and Andrew Kaido, in the more or less the same time, share the similar ideas, and Robert developed this ab initio Greg-canonical molecular dynamics, Monte Carlo, sorry. And for this method to determine the silver surface stabilities in the oxygen gas phase. And on the one hand, they use this ab initio Greg-canonical method to find the structures or find the lowest energy isomers, then use the state-of-art ab initio atomic thermodynamics to determine the surface stabilities. On the other hand, technically, I would like to discuss that from my experience that for this kind of system, that it is more easy to absorb the oxygen, but it hardly to dissolve the system, which will break the detail balance for the Greg-canonical. And in our method, we take advantage also with replica exchange. what is a replica exchange? The original idea of the replica exchange looks like this. The x-axis is the simulation times, y-axis is the different replicas at different temperatures. And the advantage of replica exchange, the traditional ones, is that the replicas at relatively low temperatures by swap during the simulation can approach the high temperature regions, which can overcome the kinetic barrier easily. And by combining the graph-canonical and the replica exchange, these two methods, we develop a method named replica exchange graph-canonical, and during the simulations that each replica is defined by two thermodynamic variables, chemical potentials and temperatures. And during the simulations, the replicas at lower temperatures has a chance to go to high temperature regions where the kinetic barrier is overcome more easily. All the configurations or replicas at higher chemical potentials have the chance to approach to the low chemical potentials where the system can absorb and desorb more easily, so that enhance the diffusion of the system. And moreover, unlike the one-dimensional replica exchange scheme, we also design 2D replica exchange scheme. And in the traditional 1D scheme, that each replica has one or two neighbors to swap with the thermodynamic state. But in our 2D scheme, and each replica at least have 3 or even more. At most is 8 neighbors to try to swap. And we also designed 4 different swap types. And in each swap type, there's collective swap for all the replicas to enhance the diffusion between the replicas. This is a flowchart of our replica exchange graph-canonical method. The required inputs are the initial configurations, the temperature range, and the chemical range. And these inputs can be determined related to your experimental conditions and the theoretical benchmarks. And during the simulations, all the replicas has X0 probability try to exchange the particles with its own reservoir. All 1 minus X0 to try to swap the thermodynamic state with its neighboring. After each particle exchange or replica exchange, parallel molecular dynamics are performed to further diffuse or relax the system. This procedure is iterated until the variable of interest reaches the equilibrium. Once we get this kind of thousands or even millions of data from the replica exchange graph-canonical sampling, the next task is, or the main task for us, is to calculate the free energy of a specific phase I at a specific chemical potential and temperature. And from the statistical physics, we know that the free energy is related to the probability to find this phase I. And here is capital R is a configuration sampled in the replica exchange graph-canonical, and the normalized in the denominator is a partition function. And moreover, here I want to notice that this Ki means the indicator for the phase I. So you always like the descriptor, always need to first define a descriptor for your phase. Then you can calculate the free energy if you know the partition function. And we adopt the multi-state Bennett-absorption ratio to estimate the partition function. And the M bar estimates the partition function by first defining the reduced potential function for the graph-canonical ensemble in these equations. Then the graph-canonical density function is just the Boltzmann distribution of this. And the partition function is estimated by using all the set of the sampling, the replica exchange sampling data, and with the partition function, the ensemble average and the free energy can be calculated. we applied the replica exchange grad-canonical to study the silicon 100 surface in contact with deuteria at gas phase. The absorption of the deuteria on the silicon surface has been studied for decades, so there's a lot of experimental data there. And for the pristine silicon 100 surface, the general agreement on the reconstruction pattern is symmetric 2x1, asymmetric 2x1, P 2x2, and C 4x2. And the experimental reported 2x1 absorption pattern is found is stable at 600 Kelvin, while the 3x1 absorption pattern is experimentally reported stable at 400 Kelvin. In order to include different reconstruction pattern and absorption pattern, we built two model systems. One is 4x4, the other 3x3, and perform individual replica exchange grad-canonical for these two supercells. And all the DFT calculations are performed with the FHIM's code. And since we have two individual replica exchange grad-canonical in different supercells, and we want to connect this all the sampling data from both cells, and we define this the unconstructed silicon 100 surface, and refers all the data to this potential energy of the reconstructed silicon 100 surface. And this kind of strategy also kind of help to circumvent the limitation of the grad-canonical ensemble, since we know that grad-canonical ensemble is fixed volume. So if we can connect the replica exchange grad-canonical data in this way, that we can simulate different volumes, then treat the post-processing data together. And here is when we define our descriptor for the microstates as a coverage of deuteria, and calculate first estimate the partition function, and then calculate the free energy at the specific temperature and pressure, we got this phase diagram as a function of coverage. And the white one is a pristine, and the dark blue is a maximal deuteria coverage. The gray region is beyond our current replica exchange grad-canonical samplings. In order to get insightful information about how the structure looks like for the microstates, and we further define two more descriptors. One is coordination histogram, the other is restructuring of silicon board. And for instance, for these configurations, for the top silicon layers, there are 3 dark gray silicon atoms, each coordinate with the other 2 silicon atoms and 2 hydrogen atoms, and the 6 purple silicon atoms each coordinate with the other 3 silicon atoms and 1 hydrogen atoms. And the coordination histogram for this configuration is 0360063. And if the silicon diamond board always form on the same side, then it is defined as ordered phase. Otherwise, it's disordered phases. We can further post-processing that we get this TP map of the coordination histogram. The default color is means that default coordination histogram, while here the default hatching type means that it's default dimerization type. And we found for this separated by this dashed scion lines, and for the relatively lower temperatures for the pristine or the full monolayer coverage, at relatively low temperatures, the surface is ordered phases, while at relatively high temperatures, the first surface is the silicon dimer boards are dynamically forming and breaking in the supercell. Given the partition function, that the phase transitions can be evaluated at where the peak of the response function, such as heat capacity. And in the statistic mechanics, the heat capacity is defined in these equations, and the energy ensemble average of energy, total energy, and the energy square can also post-processing use the M bar. And we could get the heat capacity peak as a function of pressure at fixed 300 Kelvin as an illustration here, this blue curve. And the red curve is the number of sorbed deuteria as a function of pressure at 300 Kelvin. Each peak corresponding to each phase transitions, and the TP condition at each peak is marked as a white dot on the phase diagram. With the increase of the temperatures, we can to 373 Kelvin. All the heat capacity peak shift to higher pressures as expected. Though not noticed before, the first peak is still there, while the second peak split into two peaks. So here at this specific pressure and temperature, there are three phases, surface phases coexist. So we marked as a triple points, plot as a black dot here. And further increase the temperature to 382 Kelvin. The first heat capacity peak is this pair. So there are two phases coexist. This is a critical point. We plot as a blue dot here. By connecting all the white dot in which attributed to the same phase transitions, we can get the surface phase boundaries as illustrated as a white lines here. And the black dot is the triple point and the blue dot is the critical point. And the estimated average baud life of the silicon-silicon dimer baud is longer than in the deuterium covered surface than the pristine surface, which indicates this sorbate slow the dynamics of the silicon-silicon dimer bauds. Last but not least, we want to compare the predicted power of the state-of-art ab initio atomic thermodynamics and the replica exchange grad canonical for the experimental reported two phases. One is 3x1, one is 2x1. And the dashed line is the ab initio atomic thermodynamic result, which indicate these two phases are coexist along the temperature from 300 Kelvin to 700 Kelvin. And while the replica exchange grad canonical method tells us that the high coverage 3x1 phases is relatively more stable at lower temperatures. With increased temperature, the 2x1 absorption pattern becomes more stable, which is consistent with experimental observations. The discrepancy between these two methods is mainly attributed to the unharmonic contributions are taken into account in the replica exchange grad canonical. That is a configurational entropy and the vibrational entropies. With this, come to my conclusions. The replica exchange grad canonical approach is the first principle description of surface restructuring processes and relatively temperature and pressure conditions. And the method is further extended by evaluate the heat capacity as a function of temperature and pressure to determine the surface phase boundary, including triple and critical points. And further, it's more like outlook that we are also underdeveloped that this method is to apply to more applications, such as heterogeneous catalysis, electrocatalysis, and surface irrigation. And here I would like to thank all my collaborators and the funding agencies, especially my PhD supervisor, Matthias Scheffler, and my group leader, Luca Grigelli, and my postdoc supervisor, Jens Noskov, and the experimental collaborations, Professor Ib Chekendorf, Dr. Jianbiao Fu, Shaofeng Li, and Suzanne Edison, and Matthias Sakarsky. And thanks again for the invitation, and thank you for your attention.